talk about database management systems a little bit, and relational database management systems in particular. We're going to talk about the history of database management systems. We're going to start with flat files all the way to where we are today, which are relational databases. Talk about a concept which you're going to learn how to do called data normalization. We'll talk about how do you organize and access databases. Then the language of the modern relational database, SQL. We'll actually see what some SQL code looks like. And then a very brief discussion of data warehouses and what they do. So why do we have to store data at all? It's kind of a rhetorical question, obviously. You store your data because, one, transactions don't all happen at one time, so you need to complete them at a later time, so you need to have that data to finish them. You need it because you need to follow up on your business with customers or vendors. You do it to create reports for management, and you do it to provide feedback to your people, to your customers, and to perform analyses, data analyses. So it's clear that you have to store your data. That shouldn't be a surprise. So what's a database? It's a collection of related data. A database has many different files. It has employees and customers and inventory all together, interrelated with each other. So your data is linked, and then it's manipulated by something called a database management system. Sitting between a programmer and the data is this database management system, DBMS, which controls the data and hopefully provides some security around the data. And if you're watching the news these days, that security is very important. So why is data organized into these databases? Why don't we just keep these transaction files? One, just the sheer volume would make it very hard to do business in a transaction file setting. The data would be complex because it's not all the same data. You have customers and employees, and et cetera. The database management system provides for privacy. It helps to secure it so it's not destroyed if there's a problem. Helps keep it accurate. And it provides a real-time basis. If you just had files, you would not be able to have an internet. You need to be able to have real-time databases. So let's go back in history to the start. And you have flat files. Essentially, all your data would be on a single record that's as long as you need for all of that data. In this case, this is all your employee data on a single file. It's stored sequentially, starting with 101 and going on down. Stored by employee number, sorted by employee number. If I wanted to get the 314th employee, I'd have to go through every single one of these sequentially to get to number 314. Not very efficient. So that's how flat files would work. You can sort them and work with them in a different sort fashion, but still, it's not very efficient. So that's how computers started. The other thing about flat files are each application program. You could have a transaction update program. You could have a database, not database. You might want to have a different kind of program that does, updates your employee master file or something like that. Each of your different application programs might need to access this same file. In this case, file B is accessed here and here. It's not accessed there, but file A is accessed here and here. There's no way for different application programs to work concurrently. So what you would do is you'd create multiple copies of these files. So file A would need to have multiple copies. And what happens when you have multiple copies of a file? They get out of sync. This copy is updated by this application program, and this copy is updated in a different way, and they become out of sync with each other. And so you run the risk, because of data redundancy, of having your files corrupted and not useful to each other. You want to have a single source of updating a file. And so in order to prevent that redundancy, you have very complicated application development so that things don't happen simultaneously. So that's the world we lived in. We moved to a world of a database management system where you have your various application programs, and this database management system sits between the programs and the data. So this is kind of like command and control right here. If one of the application programs is updating this file, file C, nobody else can update it until they're done. It locks other people out. And so it eliminates the need for redundancy. Now, you could have two programs accessing the same data set, but not the same record within the data set. So if one program is accessing employee number 3 and the other one's accessing employee number 2, they're not fighting with each other. But they can't both access employee number 3 at the same time. So it eliminates the need for redundancy. It creates some control. And it just makes for an easier development between your application programs. So we went from flat files to the very first type of database. And these were hierarchical database. It was an IBM product called IMS, which was the kind of the main hierarchical database of its time. 1970s and 1980s, this was the database of choice. And if you looked in major companies today, there are still many, many programs using hierarchical databases because it's hard to get rid of legacy systems. Think of it as an inverted tree, almost like a family tree. So an employee number 9, can only be in one department. A department can have many employees, but an employee can only be in one department. And departments can only be in one plant, and plants can only be for one company. And so it allows for that one-to-many thing we were talking about with cardinality, or potentially a one-to-one if you only have one employee in a department. So you have a one-to-one or a one-to-many. It doesn't handle many-to-many, the hierarchical database. It did this by having a pointer. So every employee would have a little field on the employee record that says, I'm a member of Department 1. It points to Department 1. And that's how the linkages were created. So that's the hierarchical database. It was clear that that wasn't good enough, so the next phase of databases was a very short-lived phase called a network database, which essentially was built on top of IMS, and it was the first iteration of creating a many-to-many. It kind of allowed for more than one linkage, if you would. So an employee might work in 2 different plants or work for 2 different departments, and so it would allow for more than one of those pointers, and so you could then point in more than one place. But it was something called, it was kind of kludgy. And who here has heard the word kludge? I don't know exactly how it's spelled. It's either spelled like this or like this. It's a kludge, and a kludge is an inelegant, not elegant, technical solution. So in order to create the possibilities of a many-to-many relationship, the first step was this kludgy approach called a network database. Then you went to a relational database. Notice when they were first designed and developed, 1969, even before hierarchical databases were in vogue. So the concepts were there. The reason it wasn't until the 1990s, and really the mid to late 1990s, that these actually took hold is because, anyone want to take a guess why? It's because the hardware wasn't fast enough to be able to do this processing. These things they just took more resources to do right, And it took time for the hardware to catch up to the software. And in the mid-1990s, caught up. Remember, I think I told you guys, when I first used Microsoft Excel, I'd hit enter, and you'd see the little thing going around and around and around and around and around and around and around until it updated your one little field. It's true. The hardware caught up in the 1990s and then went well past it. Because in fact, relational databases are not much different than Microsoft Excel. You know how Excel has worksheets and tables? Each table in Microsoft Excel is an object for a relational database. And when we use Microsoft Access, it's actually built on the same technology model as Microsoft Excel. It won't look like it, but it is. And it's all built with two-dimensional tables, and a lot of two-dimensional tables. And so even though relational databases started in 1969, they took a while until the hardware caught up and they could be used. One of the nice things about relational databases is relationships can change over time. You can change a relationship on the fly. So let's just say it used to be that an employee only had one of these things, but for some reason Rutgers changed their mind and said they want employees to have two of them. You can change that from a one-to-one to one-to-many relationship on the fly. If you used a hierarchical model, you'd have to take the database down, do a whole redesign. It was much, much more difficult. So you can define relationships far more easily in a relationship model. It's the most widely used database management system today. The main systems in the production world are DB2 from IBM and Oracle. Those are the two main ones. Microsoft Access is not really used by large companies. It's meant for individuals, really. But it's a very good surrogate for us to learn the concepts behind it. It works in much the same way. Talking about relational database systems, the fact that they've been around for a long time, they take up more processing power than some of the hierarchical systems or flat file systems, which is why it wasn't until the late 1990s that you saw them become the database system of choice. And now pretty much everyone uses relational databases in any new build. So the trade-off with relational databases, it's not the most efficient way to build a system. It takes a lot of computer resources because of all the linkages. However, almost everybody in today's day and age of hardware and software will accept the lower efficiency in the use of hardware for the improved ability, flexibility, and speed, not speed, but flexibility and ability to get information out of that system. So you're making the trade-off of efficiency versus flexibility, and because of the nature of hardware today, flexibility can win without really anybody noticing. Okay, let's talk about relational databases. Think about your Excel spreadsheet. You have rows and you have columns. That's what an Excel spreadsheet is. That's what a table is. So every table in a relational database is like a worksheet in Excel. Each column is an attribute. It might also be called a field. In relational database, you call them attributes. You tended to call them fields in the older style databases. Each row is a record. I'll never use this name again, but you'll see it somewhere. It's also called a tuple. A row is sometimes called a tuple. Rhymes with couple. So you would have each record would mean each one of your employees would have a row, and each column would be their attributes, their last name, their first name, their address, their billing rate, their what department they're in, etc. So the columns are their attributes, the rows are the individual records. Each row will have some type of a primary key, which makes it a unique entity in the table. Employee number, might be the unique key for employees. You might use social security number, although we've said it's not absolutely unique, but close to. Last named is not a good key. Of course, there are a lot of Smiths in this world. And so that's your primary key. Your foreign key is what you use to relate one table to another table. It is the link between tables. Anytime you have a foreign key on one table, it points to a primary key on another table. And that's how you link them together. So this is what a physical design of a database might look like. Not a logical design, a physical design. And this I took straight out of your textbook, which is why it's a little bit confusing. Before the open parentheses, this is the table's name. If you would, the worksheet name at the very bottom of, of your Excel spreadsheet. So customer might be a table. Each of these things is an attribute, a field. There are two ways that you will see primary keys specified. Again, two different books, two different ways of doing it. In one book, your primary key is underlined. I'm pretty sure this is coming from Cybertext. And the other one will be Chang. In Chang, your primary key is double underlined. And then you have your foreign keys. In Cybertext, it's an asterisk after the attribute name. And in Chang, it's a single underline. Don't care which one of these you used, you just need to be consistent. So here, order number, single underlined, is your primary key. Almost always your primary key should be the first attribute you see, but it doesn't have to be. There's no rule that it has to be first, but almost always it will be. This doesn't look like an asterisk there. It looks like just a spot on the screen, but that is in fact an asterisk. And so customer number is a foreign key that points to the primary key, customer number, on your customer table. And so you can then find all the sales orders that a customer had made. The sales order also has a region number as a foreign key. It has two foreign keys. You have as many foreign keys as you want. That region number points to the sales region table, so you can then see how many sales orders you have per region. Look at this one here. Order number, item number. They're both underlined. That is two fields, two attributes that together are a single primary key. That's called a concatenated key. I think I mentioned it at the beginning of the class, but you mentioned it again. You will see concatenated keys quite a bit. Concatenated keys are used as a means of relating many-to-many relationships. So this is telling us an order, a sales order, can have many items in it, and an item could be in many different sales orders, right? You sell bananas to many different customers, and a customer could buy lots of different fruits, not just bananas. So in this case, we're showing it the way that Cybertext shows it. They underline it and they asterisk it. You can just underline it, that's fine for me, okay? You can do both if you want. Doesn't add anything. So, and these lines that we have here, this is not really part of the physical design. This is just for you to see, so you can see the relationships that the physical design is creating. So in phase 2 of your project, you will be producing something that looks like this. So what are some of the rules for relational databases? Every table name must be unique. You can only have one table called the customer table. Every table has to have a primary key. And each primary key has to have a unique value to it so that you won't have duplicate rows. Right? You can't have two customers with the same customer number. You have to have different customer numbers, otherwise you have a problem. That's the primary key. Similarly, you cannot have two columns with the same name. So a lot of addresses have two different lines before you get to city and state. You can't call them both customer address, customer address. You have to have customer address 1, customer address 2, so that they be viewed as different columns. But the order that you put them in doesn't matter. That's the beauty of a relational database. You don't have to store them in ascending primary key order. They'll figure it out. You don't have to put address line 1 before address line 2. It's a good idea, but it'll work just fine if you don't. So let's go through some of the key concepts of databases. Some of this we've done already, so we'll just be seeing it a second time. First is the data hierarchy: bit, byte, field, record, file, and database. Bit, what are the values for bits? 0 and 1, on or off. How many different bytes can you have? No, how many bits in a byte is 8? How many different 2 to the 8th? 256, 2, 4, 8, 16, 32, 64, 128, 256. Thank God it's not. Thank God they don't have 12 bits, because then I'd run out of fingers. And no problem. Field. What's another name for a field? The name that we use with relational databases? It's an attribute. A field is an attribute. A record. What's the name another name for records? It's a row, or the word that I won't use anymore, but you can. Tuple. Tuple rhymes with couple. A file is really a table. And then you have your database. So a record structure would just be a series of attributes related to a specific occurrence of a record. In this case, it's Terry Smythe or Smith. Keys. Every table must have a primary key. Every primary key must be unique, whether it's a single field or a composite or a concatenated field. So you will see situations orders and items. Remember, we had that as a concatenated key. Let's say banana is item number 1. And apple is item number 2. And you have two orders, A and B. And then you have this table called your order item table. And it has as its primary key order number, which is really a letter, item number, both of them underlined, and then whatever other attributes are appropriate, doesn't matter. Let's say each of these orders had both items in it, okay? So you would have 4 records. Okay, your first record would be order A with item number 01. Your second record would be order A with item number 02. Those are the two items they got. Notice that A is repeated, but that's okay. The order and item together is unique. Then you'll have order B, item number 1, and order B, item number 2. Again, now you have the item numbers repeated here, but that's okay because the concatenated key, order and item number together, is unique. That has to be unique. The concatenated key has to be unique. Okay? Let's talk about keys. In this case, we say it's not necessarily the best way to do it, but Social Security number is the primary key for your employee table. And you also have a department table where A is the primary key. It's just a department letter. Department code here is a foreign key on the employee table that points to a primary key on the department table. What that allows you to do is you can produce a single report with information from this table and this table together. It allows you to link the information. So you have whatever, somewhere here would be Terry Smythe, her department. Notice there's nowhere here where it says who her manager is. You get her manager by linking to this table and seeing her manager there, etc. So the value of the foreign keys is it allows you to link information between two different tables and bring it together for whatever purpose. Could be for producing a report, could be doing for analysis, doing math, whatever you need to do. So that's how a foreign key works in a relational database. Relationships, cardinality. We started on this on Monday. There are 3 cardinalities. One to one, one to many to many. I'm just showing you this. There's no difference between 1 to n and 1 to m. Sometimes you'll see it with an m, sometimes you'll see it with an n. It doesn't matter. N to 1 and 1 to n mean the same thing. Don't even think about that as something important. They're the same thing. And then m to m, m to n, or n to n are all the same thing. That's a many-to-many relationship. So because we have 2 texts and they don't exactly do things alike, we just need to think about kind of different iterations of the symbology and the nomenclature. It's called cardinality. You're going to either love or hate cardinality. Data redundancy. The value of a database management system is it prevents data redundancy. It's something you want to avoid in a well-designed database. Flat files, we said you have to have fields multiple times in different files. The only time you'll have an attribute on multiple tables, if you do your design correctly, is it'll be on a foreign key on one table pointing to a primary key on another. So that department attribute occurred on 2 different tables. But its occurrence on the second table is only as a pointer to the primary key of another table. You don't want, you would not, it would be bad design, and it would be bad design to repeat all of this information here. Because if they change department A, they fire right, and they bring in wrong, like that. They bring somebody else in. You have to change every single one of these records. So you just have, the only time you have redundant data is just as a pointer to this information, so that you don't have to worry about getting your data out of sync. Because redundancy creates the risk of having data inconsistencies. Concurrency says you can't have 2 different users accessing with the ability to write data to the same record at the same time. Because if I'm writing to it and you're writing to it at the same time, the database could get all messed up. It'd be kind of like if we both went on to Expedia and wanted the exact same seat on an airplane at the exact same time. So as soon as I get in there to take a seat, it's got to lock everybody out of accessing that airplane at that moment until I'm done. Otherwise, you run the risk of two people going for the same seat. The computer gets all messed up, and then you don't know what to do. So you don't want to allow, and the database management system does it for you, it does not allow multiple users to access the same data record, at least for writing purposes. You might be able to read it multiple times, but for writing purposes, you want to limit it. That's all it says here. The database management system does that for you. Okay. So we talked about a little bit about cardinality. Something else that you will learn how to do in this class is something called data normalization. This is actually how tables look on Microsoft Access. So when you're doing the implementation of your system, you'll be creating tables that kind of look like this. Data normalization is the process of making sure the right attributes are on the correct records. And they're on there only one time. So you want to make sure your data is in the third normal form. It's called the third normal form. There are actually 7 levels of data normalization. Levels 4 through 7 are irrelevant. They're not only irrelevant in our class, they're irrelevant in the real world. Companies, as we will, are only looking to get to the third normal form. So we won't learn 4 through 7. The 3 levels that we will focus on in chapter 9, I think, we will eliminate repeating groups of data so that data will only occur once. Well, eliminating repeating groups of data gets rid of flat files. Eliminating redundant data ensures that data only occurs once. And then finally, we're going to eliminate the situation where an attribute does not relate to the primary key. It relates to another field on the record. I don't want to get into this right now. So don't worry about this third normal form. Right now, we will get to it, and you'll understand it in detail when we get to chapter 9. Referential integrity. Referential integrity simply says you cannot have a foreign key that points off into space. So if you have a foreign key on this sales order that's pointing to customer 123, you better have a customer with a primary key 123. If not, your database is corrupt. So referential integrity. Says you must point to a real record somewhere else if you're a foreign key. Data validation. Seems kind of odd to have data validation in this chapter at this moment. Seems like it's a different conversation. But the reason we have it here is that data validation in a database management system is inside of your data. Your data. There's something called a data dictionary. Data dictionary. That for every field or every attribute gives you information about that attribute. That's called metadata. Metadata. Which is data about data. Sounds kind of like double talk. But let's just say you have a field or an attribute called Social Security number. That's your attribute. There's information about the Social Security number. It's 9 characters long, which means we're not including the dashes. The dashes are implied. But in the database, we're going to store it as a 9-character numeric field. It says text here, but somewhere you can have a validation, right? There's a validation rule right there in the middle of the data that says it must be numeric. Okay? So this is metadata. It's defining information about your Social Security number. And there's a lot more detail, range. Social Security number would not have a range, but maybe if you're buying something from Amazon, they may have a range that says, you know what, if someone's trying to buy more than 20 of a given item, let's reject it, because they probably typed something in wrong. So they might say 1 to 20 is your valid range to buy cameras. Okay, so this is your metadata concerning the field Social Security number, and that's done inside of a data dictionary, which describes the data in the database. There's a person called a database administrator, makes pretty good money, by the way, who's responsible for owning the data in a database. Database administration, every large company has a significant database administration organization. The other thing they do besides describing the data is they give permission for the data. Depending upon who you are, what department you're in, what level you are of the organization, you might be allowed to look at some data, you might be allowed to change some data, you might be allowed to delete some data, but it's up to the database administration function to give that permission to individuals. So here are some of the validations that you could have in your metadata. A range test between 1 and 20. A validity test. You could, for instance, if you had a field on your customer database called state, you could allow only 50 values, NY, NJ, NE, whatever the 50 states are, right? And that way, if somebody tries to type something in, more often than not, it's a list. But if somebody wants to type something in, and they try to type something in that's invalid, it will be rejected immediately. A length test, where the correct number of digits entered. Do they enter 9 digits for the Social Security number, or do they only enter 7? This is very important for when you enter your credit card number, for instance. And a valid combination test. An example of a valid combination might be taking a zip code and comparing it to the state that you put in. Did you put in a zip code for the proper state? If not, say zip code, you want to tell them zip code and state don't match. So those are validation rules that can be in your data. Data querying language. This is kind of that 4th generation language that we talked about in chapter 3, I think, that allows you to query your database. The most well-known, the most popular one today is SQL or SQL. In fact, when you do your work in Microsoft Access takes kind of the commands that you give it, which are really a bunch of clicks. You're clicking more than anything, Microsoft Access, and converts it into SQL, which then gets compiled and assembled and becomes zeros and ones. So the first step is to take this 4th generation language and get it in there. There are 4 main operators. You select, insert, update, and delete. And let's look at some SQL. It's fairly English-like. Let's start off by looking at our tables. Same 4 tables we had. You have a customer table, a sales table, an item table, and an item sold table. Item sold relates the sales and the items table in a many-to-many relationship. And you see that the customer relates to everything only through the cell, as a foreign key on the cell points to customers. So let's just say you want to know which customers have exceeded their credit limit. You would actually create an SQL statement, a SQL statement that looks like this. Select from customers where credit limit is less than balance. So you just go into the customer table and you want to dump out a list of all your customers where the credit limit is less than their balance. They've exceeded their credit limit. Goes to only one table, right? Doesn't even care about these other tables. A very simple one. So get the second one. What are the names and phone numbers of customers who have been sold merchandise by John Doe, one of your salespeople? So that's your salesperson. So you want the name and phone number. So you want to be able to figure out all the people, all the customers who have bought something from John Doe. And then when you do, you want their name and phone number. Maybe they found out that he was stealing or something, and you want to call them and say you're sorry. So let's look at how SQL looks here. Select customer name and customer phone number, those 2 fields, from your customers and your sales tables, where your customer number here equals this, so that the primary and the foreign key are equal, and your salesperson here has the name John Doe. So you find all you go through your sales file, sales records, until you find something with John Doe. You're then going to take this customer number, point up there, and grab their name and phone number. Here's a third one. Why don't you take a look at it? What are the names and balances of customers who have been sold item number 1250? So it's a good question. You can link multiple tables together to get at the information you want. So what's happening here? We're selecting the 2 fields we say we want, the name and balance for customers who have been sold item number 1250, and we need to use the customer, the sales, and the item sold tables. So let's start at the bottom here. First you're saying we want to find the item sold from the item number table, 1250. Then from there you get to figure out the invoices from this table, from the item sold table. And then from there you find the invoices and you get the customer number. And from the customer number you can then get the name. So you almost could read this bottom to the top to see the flow. Okay? Here's the good news. You don't need to do this, right? Microsoft Access is going to do all of this for you. Data warehousing. So in an ideal world, every company would have one really large transaction database that has all their divisions in it and all the different information that they need in a single database that they can run real time and do their transactions off of that database. That's the ideal world. For a variety of reasons, that's not possible. A lot of companies are just too big. The database would be too large and unwieldy. In some cases, the people are all over the world, and getting it all synced up would be very difficult. A very important problem is every company has built their computer systems at different times using different technologies and different systems. And to try to link that all into a single database would be prohibitively expensive. So companies have multiple transaction systems all over the place. That's just the reality of the real world. Nothing is as perfect as it should be. So that's where data warehouses come in. Data warehouses take the important information from all of these different systems, may combine it with outside information, and puts it into a data warehouse. A data mart, M-A-R-T, data mart, is very similar to a data warehouse, except it has information from outside the company as well. It may have weather information in there if that's relevant to you. You can have whatever you want. But a data warehouse takes the important information from all over the company's disparate systems and then makes it available for analytics, to do the analyses that you want to do to kind of get ahead of the competitors, if you would. So in today's day and age of big data, everyone's doing this. So creating the data warehouse, you have to build the database, identify what data you want in a data warehouse. Then you figure out where you're going to get it from. And that's a lot harder than you think to get that data. This next point seems like it would be easy, but it's quite difficult. Standardizing the data so that all your different systems, some systems might have customer numbers with 7 digits, others may have 9 digits, some could be alphanumeric. The same customer can have different coding in different parts of your company. So back in 2008, when everyone was trying to figure out how much exposure they had to AIG, because AIG was about to go under before it was saved, needed to go all throughout the company and find out their total exposure. And it might have been called many different places in many different parts of the company. So you want to figure out how do you get that data. You want to standardize it. And so you say, we're going to use the format of 1, 2, 3, 4, 5, 6, 7. And then you do something called scrubbing the data. Scrub. It's just what it sounds like. You clean it. Because this data is going to have all kinds of junk in it. And you have to clean out the junk. And then when you've done all that, you then have data that's ready for your data warehouse. You have to go through all those steps. It's a lot harder than just taking the data from all your databases that you want and just putting it all together. In an ideal world, it would be easy. But because of the nature of how computers have been built over the last 40 years, it's not as easy as you would think. Data mining is the process of using that data, right? You're not putting it out there just for no reason. That's your analytics. And you use something called OLAP, Online Analytical Processing, to do that. You may want to drill down. How much do we have outstanding? What's our risk with AIG? You drill. You may want to consolidate. What's our risk to the energy industry? Energy is struggling. What's our risk to the energy industry? Pivoting. How many of you have used pivot tables on Excel? Anybody? A few of you. So that's you're pivoting. You take the data, you combine it, it summarizes it in a certain way. It's a very nice function on Excel. You might do that. Time series analysis. On your data warehouse, you're not just going to keep the current data, but you may want to keep last year's data too. So you can say, how are we doing versus last year? Exception reporting. Have we ever done a transaction for more than $10 million with anybody? Who's it with? And then what if simulations? What if our exposure to AIG were increased to $500 million? What would that do to us if they went under? So as you maybe have a big transaction you're thinking about doing, and you'd want to do a simulation to see what that would do to your company's situation. So that's data warehousing. So you have your databases, some things you need to do to your databases. You need to back it up from time to time. A static backup means you just take the whole database and you dump it to a tape, and then you send that tape off to Utah, and you hope that it will survive the next nuclear explosion. Because it's very important to have your data after that nuclear explosion. A dynamic backup occurs on a transaction-by-transaction basis. So as you write the transaction, you write a copy of it somewhere. One way of doing dynamic backups is RAID technology. We mentioned it before. And when I mentioned it last time, I said, I don't remember what it stands for. Now I remember, because I wrote it down. It's a redundant array of inexpensive disks. Redundant array of inexpensive disks, RAID. So you have multiple disks at the same time. Every transaction is written to more than one disk. Generally speaking, you want to write it to an odd number so that if two agree and one doesn't, you trust the two and assume that the one that didn't agree had some kind of corruption. So RAID is not used to increase your data storage capacity. It's used to create fault tolerance, being able to handle a problem. And then we talked about concurrency control. The DBMS does that for you. It might lock you out completely, meaning no reading, no writing, no nothing. Or it might just prevent more than one user from writing to a record at the same time.